Okay. So today we will go for online session. So easier for you all for those who on leave those yang celebrate Selamat Hari yang Raya Haji Okay. So these topics you will have last last week right? Yeah, you all have the three-level factorial design, and you will have one question on that. Okay, and another questions will come from this topic. That's why very important. Okay, so in these topics, I will cover the methods of steepest essence and response surface methodology. So like what I mentioned that day, two-level factorial is used for screening of the factors. Okay, those are significant factors. Then after you do the screening and you have select the factors, then you will need to do you will start to find the optimum range. Okay, range not the point so you will find the optimum range of your factor. In this case, you will need the steepest of method of steepest essence to find the range that near to the optimum point. Yeah. After you find the range, then you will find the optimum point of your factors. That will involve response surface methodology. Okay, these are the five main DOE stages. Okay, yeah, this is important. This is important. So in screening, normally you will use the two-level factorial design, and you will screen, for example, if you screen for 10, 20 factors, you will need you won't use a full factorial design, full two-level factorial design, because if you use the full factorial design, you will need to run a lot of experiment runs. So in this case, you can use fractional factorial design. It is also a two-level factorial design, same like the two-level factorial design. Just that the experiment runs that you need to you need to conduct is lesser. For example, 1/3 of the experiments to screen out which factors are significant. After that, you will do characterizations where you will study, you will confirm whether the factors that you have selected are significant or not, and whether they have interaction effect or not. Then after that, you will go to improvement, where you will use the method of steepest essence or distance. Because why is this essence and distance? Because your response not necessarily you get the maximum. Sometimes you want to get the lowest is the better for you, then you will go to find the method using the method of steepest distance to find the lowest point, lowest range. Okay. In After you find the optimum range, then you will do optimizations to find which point is the best to give you the highest or the maximum output. And in this case, you will use the response surface methodology design. Okay. After you do the optimizations, then you need to do verification. Because in optimizations, after you run the experiments, the software will do a prediction. So they will predict which optimum condition is the best for you. And this is just prediction. Yeah. Although you have run a series of experiments, uh, according to what the software gives you. Okay, after you run the experiment, you key in the data, then the software will do predictions. They will predict this is the optimum conditions. For example, the pH, they will predict pH 7.1, temperature 27.5 are the best with this combination. You will get your maximum yield. Okay. Uh, however, this is just prediction. So you need to run a verification experiment where you will run again the experiment with the predicted condition, where the pH is 7.1, temperature is 25 point. Just how I said what 25.7 or what I forgot. Yeah, according to the predicted values that given, and you need to run the analysis and find and compare the predicted values given by the software is the same as what you obtain in your experiment or not. Yeah, once you confirm it is about the same. Yeah, for example, 20% within 20% or 10% difference, then it's good enough to show that your optimization successful. Okay? So we will use the Design Expert version 13 for your practical next week. Okay. So next week you will do the practical, and your practical you need to uh, do assignments. Okay. It's just some sort like report, and this report is your assignment. Okay. And we need to separate into group. That day we already mentioned, right? How many person in one group. Yeah. So you all have to form the group for the practical. Okay. We will go more details on screening. Okay. So the screening is normally you will screen those unknown factors. Okay. So those known factors that you already know that, okay, for example, you're making noodle, you know that you have to put in the flour. Okay, the flour is 10 gram, so you won't change that. If you already know that this must be added and this amount must be added, then you do not need to screen this factor again. Yeah, you just need to screen those factors that you are still unsure. For example, you know the butter is one of the ingredients, but you don't know how much of the butter you should add in. Yeah, then you have to do the screening on the amount of butter that you have to add in the recipe, for example. Okay, so during the screening, when you do the two-level factorial design screening, so there are some factors contributes more to the output, the outcome, and there are some factors that even though it has positive effect, but it just contribute very little. And normally, when we do the optimizations, we won't select those factors that contribute very less to your output. For example, uh, making noodle, it just contribute a little of flavor or texture to the noodles, although it has positive effect, but we won't consider that. Yeah, we will find those factors that contribute the most. Yeah. So in this screening, we will, for example, we will get C, which contribute 41% to your output. We will select B, which contribute 36%. We will use D, where it contributes 10%. And you can see that all the factors, some that have interaction effect, they will interact each other, okay? Some just interact in one way. B affects C, but factor C won't affect factor B. Yeah, and there are individual factor where other there is no interaction with other factors. Yeah, for example, D in this case. Yeah. Okay, so screening is just to narrow down the vital few lah. Meaning you just select the important factors, not all the factors. Yeah. Okay, there are many types of factorial design to be used for screening. One is two-level factorial design that you have learned. Another is minimal run screening design. There are Brackett-Berman or Taguchi as well. These are some of the design, yeah, that can be used for screening. Yeah. Okay, this version is version 7. Yeah. I didn't update the version 13. I should update that. But you can see the software have evolved from during my time I used version 6 and then 7, 8. After that I jumped to 11 and then version 13. So you can see the interface changed a lot. Yeah. So two-level factorial design. Yeah, you can see the white color column is the full factorial design, meaning you run all of the experiments. So the green color, yellow color, and red color is the fractional factorial design, where you just run a portion of the experiment runs. Yeah. Okay. So characterization is to characterize the significant effect and the interaction effect. Okay. For the one that you have selected from the screenings, for example, you have selected 4 factors from the screenings, and you will need to double confirm whether there is a main effect, interaction effect or not. Yeah. So once you identify this, then only you continue to improvement. Otherwise, when in this characterization, if curvature is not detected, then it's difficult for you to find the range later. But you still can find the range using the improvement. Just that you will take more experiments to run to do it. But curvature is not important in here, yeah, because you have the improvement to find the curvature later. Yeah. So the main goal for characterization is find the main effect and interaction effect. Make sure that you are double confirm whether it's significant or whether they have the interaction effect or not. Yeah. Because just now you during the screenings you maybe have 10 or 20 factors, so that the software might tend to have error, yeah, when they select those factors. That's why you need one more step to confirm the one that you selected from the screening. Yeah. So normally in characterization, we use the full factorial design. Okay. The white color one that I show you, meaning you run all the experiments because you have selected 4. So, or 3 or 4 lah. So the experiment runs actually lesser. Yeah. So you double confirm with that. Yeah. Fractional factorial design will give you what to find out the factors, but because you have cut short many experiment runs, you have removed many experiment runs, so they tend to have error lah. That's why you need here to confirm. Yeah. Okay, so screening and characterization is to find whether it's significant or not. Okay, so you can see if is the line is going up the hill or going down the hill. Yeah. You will you will confirm whether it's significant or not. Yeah. If it's a straight point, yeah. How should I draw the oops, I cannot I want to draw on the screen, but let me share again. Um, cannot. Okay, never mind. Can't draw some anything here. Yeah. Oh, here. I don't know what I picked here. Okay, never mind. All right. So once you find the significant factors, then you will go for improvement. Okay. Improvement is you want to find the range where is near to the optimum point. Okay. So just now the line is going up the hill. Now you will try to find improve so that the range is near to the optimum point. Optimum point is the pink color dot lah. So the pink color line is the one you do the improvement to find this range. Okay. So using the method of steepest ascent, you were able to find this range that near to optimum point. Okay, I give an example. Normally, when I give example, meaning it's important. It's very important. So, for example, here, a chemical engineer is interested in determining the operating condition that maximize the sugar content. Two controllable variables affect process yield. The first factor is the hydrolysis time. The second factor is hydrolysis temperature, and your response is the sugar content. So in this case, the engineer currently operate in the process with hydrolysis time at 35 minutes and temperature of 155 Fahrenheit. Okay. And with these operating conditions, the sugar that they obtain is about 40%. Okay. So now the engineer decide to explore whether this range, okay, this 35 minutes and 115 is considered optimum or not. Okay, then the engineer decides to find using a range, because currently it's using 35 minutes, so the engineer try to use a range 30 to 40 minutes. Okay, and also the temperature 155, then the engineer use 150 to 160 Fahrenheit. Then they do some screenings. Okay, do some screenings. So when the engineer key in the data in the software, and the software give a different experiment runs. Okay, this is factor one is the time, two is temperature. So in this case, yeah, you need to calculate the coded variable first. Because in the equation, normally they are using coded variables instead of the actual variables. But what we call it coded value and actual value lah. So 30 minutes to 40 minutes is the actual value. 150 Fahrenheit to 160 Fahrenheit are the actual value. So coded value will be -1, 0, and +1. +1 meaning the highest value lah, where the level. Okay, okay, we go back to the level. 3 level. I mentioned high level, mid level, or low level. So high level, for example, at this hydrolysis time is 40. Then the coded value will be +1, +1. So 30 minutes is the lowest point. It will be -1. Then 35 will be the center point, will be the mid, will become 0. Okay, the coded value is 0. Okay, so how it calculates is they are using the real value minus the center value, then divide with half of the range. But you do not need to care about this. Yeah, you just know that if the 3 level, high level will be +1, middle will be 0, and the lowest will be -1.
Dengan bawah tu. Tolonglah buka lampu balik. Kau tengah.
Ya, siapa tengah tembang panas nak. Kena mute lah. Okay. All right. Okay. After this part, we take a break lah. After this part, because this is important, surely will come up. Okay. For example, if I give you this kind of table, okay, so you have the actual value and the coded value. So like I mentioned just now, 30 is the low level, it will be -1. 40 is the high level, will be 1 or +1 also can. 35 is 0 because at the middle. Yeah. So let's say the engineer has run the experiment and they get the sugar content. These are the sugar content. Then they need to find the first order model here. Okay, how to find the first order model? Okay, this is very important, super important. Okay, take note. You have to know how to calculate the first order model here. If I give you this kind of table, then how you going to generate one come up with one calculate one first order model equations? Okay, so normally we will have if first order model, it will be y equal to coefficient plus coefficients factor 1, okay, plus coefficients factor 2. Then you will get a straight line, first order model straight line. So to calculate the coefficients, you have to average the response, okay? You have to average out the response, then you will get this. All the response are the whole one. Yeah. Then you plus this red color will be using the coded value -1 times 39.3 plus -1 times 40 plus 1 times 40.9 plus 1 times 41.5, then divide 4 because we need the average. Okay, so divide 4, then you will get the red color for factor 1. So factor 2 will be the same, using -1 times 39.3 plus 1 times 40 plus -1 times 40.9 plus 1 times 41.5, then divide 4, you will get the value for factor 2. Okay. So if you want to calculate by yourself now, also okay. Do you want to calculate by yourself? To try? No. If no, then I will show lah. Okay. So after you calculate, you will get 40.44 plus 0.775 for factor A plus 0.325 for factor B. Yeah, you can calculate and see whether yours is correct or not. Yeah, I give you 5 minutes to calculate. Yeah. Yeah, you should be using this. If you cannot get the similar value like I shown just now, then let me know. Okay, I will explain again. Yeah, 5 minutes. Oh yeah, please sign your attendance online in the e-learning. Okay. Can I? So if no question from you all, meanings I believe you can calculate and get the similar values from like mine. Okay. Okay. So next, if after you get this equation, now with this equation, how you going to find the which range is the best, right? You only know this first order model, and you still do not know where is the range, which range is give the highest sugar content. So by using this first order model, you can actually do steepest ascent method, okay, method of steepest ascent, start to find the range. Okay, how you going to do that? Okay, in theory, actually in the books lah, normally they will teach you using this method. Convert coded value first, then find other ways. But for me, I will tell you direct go to the example 2. Okay. This example 2 is one of the fastest way to do the method of steepest ascent. Okay. For example, you have now we don't look at the 40.43, okay? Because we want to know the factor 1 and 2 here. And let's say what is the range for factor 1 and what is the range for factor 2? In this case, okay, let me tell you, 0.775 and 0.325 are the coded value. Coded value. So in this case, you have these two for factor 1 and factor 2. And now I want to find out whether where is the optimum range. So I use 0.775 divide with 0.775, then I will get 1. Okay, This 1 unit is the coded value for 1. Okay, when I move my factor 1 for 1 unit, my factor 2, this one is factor 1. Okay, my factor 2, you will be using 0.325 divide 0.775. Then you will get 0.42 units. Okay. Okay, in this case, meaning when I move my factor 1 for 1 unit, then my factor 2 will move 0.242 units. Okay, remember 1 unit and 0.42 units here, yeah? Sorry. Is it? Yeah, correct. Okay, this is what I mentioned. When 0. For factor 1, when move 1 unit, your factor 2 will move 0.42 units. So this is in actual value. In this case, we go back to the ones here, okay, to this table. We know that this time and temperature, okay, Fahrenheit, this Fahrenheit. So I know low level is -1, mid is 0, high is 1. So just now mentioned factor 1 move 1 unit, meaning that 0 to 1 unit. This is 1 unit, move 1 unit. Okay, the mid value, actual value is 35 degrees Celsius. Sorry, minutes. Low is 30 minutes. This one is 40 minutes. Okay, 35 to 40, meaning one unit, 0 to +1, it will be from 35 to 40 minutes. So what is the range here? 0 to 1 is 5 minutes. So we know that 1 unit for the time, for the coded time, is equal to 5 minutes of the actual value. Okay, clear? Same to the temperature. Temperature low is 150, is also -1. Mid, this is actual, actual, and this is coded. Okay. Mid is 155, this is 0. High is 160, +1. So we know that from here to here, it will be, okay, 0 to, it is 155 to 160. So it is 5 Fahrenheit, 5 degrees Fahrenheit. But just now when we say x1 is when they move 1 unit in the coded, means it moves 5 minutes lah. X2 will move 0.42 units. Okay, So 5 Fahrenheit is 1 unit for x2. So 0.42 will be 2.1, right? So 0.42 units, this one is 1 unit. This is 1 unit. So 0.42 units, it will be 2.1 Fahrenheit. Okay. Sorry, it should come here. 0.42 units for factor 2 will be 2.1 Fahrenheit because 5 is 1 unit. Yeah. So now we know that when x1 move 1 unit, it is 5 minutes. How come? Then while x2 will be 2.1 Fahrenheit. So we know this already, the relationship. Then we know that we can come here. Okay, the difference each step, each step. Let's say in this coded variable, when I move 1, my x2 will move 0.2, meaning when I move in the actual, when I move 1 unit is 5 minutes. 5 minutes, correct. Then this is 2.1 Fahrenheit. But I just make it easy for calculation. That's why I put 2. Okay. It based on calculation, it should be 2.1. But I make it 2 easier. Okay. Then I can move now using 35. Okay, start from 0. We start from 0, which is 35 minutes and 155 Fahrenheit. So now we move one step, meaning I will add 5 minutes. 35 plus 5, you will get 40. 155, you put 2.22 we put 2 you will have 157. So this is one step. So you keep on do 2, 3, 4, 5, 6. So you just plus 5. Here will be plus 2. Okay, keep on plus like this. Yeah. So you will do your experiments. Okay, step by step, do that. And then after you do the experiment, you do the analysis, do the experiments and do the analysis. And you will, let's say after you do the analysis, the sugar content keep increase until a stage where it start to drop. This increase, the sugar content from here keep on increase, your response keep on increase until a stage where the sugar content decrease. Okay, this will be your range for your optimization. You will get a curvature here. Yeah, you will get your curvature graph here, because here is the highest is, let's say 30, okay, 0.3. Here is the 77.6. Here is 76.2. Now I know that I already achieved a curvature here. So from here, I just need to find where is the optimum point. Okay, where is the optimum point? So after the steepest method of steepest ascent, you already get the curvature that it surely the optimum point is inside this range. Okay, because I know that surely within 77 to 78, because the highest is 80. So I know that I know that this range is the one that I can use for optimization. Okay, 80 degrees minutes and 90 minutes. Okay, this range that 173 and 177, this range, it will cover the highest, yeah, optimum. But we still don't know lah, from 80 to 90 whether it's 86 or 80, 83, we don't know. So, but this range definitely you will have the highest already. Yeah. So we know that this range definitely you will have the highest. Then you will select this range to run the response surface methodology, run the optimization. Okay. Like just now, step one, step two, right? You keep on increase. Now until here, I know that this range is where the optimum point definitely will be here, here, somewhere this range. Yeah, this is the function of method of simplest access. Okay, okay, we break for 10 minutes. We break for 10 minutes. Now it's 3 o'clock. You can come back at 3:10. Okay, after 10 minutes. Okay, we continue so that we can finish by before 4 o'clock. Okay. Okay, for optimizations, just now already mentioned you have find out the regions, okay, the range of the factors. Now, so this just now you already find the range. So now we want to find the optimum point. So using finding the optimum point, you will need response surface methodology, where you have learned using the three-level factorial design is one of the methods or one of the design to do optimization. Okay, but like I mentioned in the class, three-level factorial design is a very old design. We seldom use nowadays. So the current design that we are using is central composite design or box Banken design, yeah, CCD or BBD. Okay, why do we need to do optimizations? Yeah, optimizations is later I will cover why you need to do the optimizations. Yeah. Okay, what parameters to consider during your optimization? First, you have to know the factors, and you have to know okay, whether the factor is significant or not. Okay, first thing. Second is your factor range, because if you do not know the factor range, then it's difficult for you to find the optimum point. Because let's say you find the range is at here, okay, you find the range is at this range, so no matter how you run, you also cannot get the optimum point. So in this case, you need to know the range. In this range, it must contain the optimum value here. Okay. So first is the significant factor. Second is the range. Okay. Okay. RS mathematics, you know that when there is power 2, it means that is polynomial. Yeah, is polynomial. Sorry, this. Okay. Meaning there's curvature lah. Okay. Sorry, power 2 is here. Okay, so after you done the screening improvement, then finally you achieve here. Yeah. You achieve the optimum point. So in the response surface, the red color is the one that is the highest lah. Blue color is the one that is lowest. Yeah. Saddle point is not the good response surface, okay, because you do not know where is the highest or where is the lowest. Yeah, so it's not a good good range, meaning the range that you select is wrong here. Yeah, this two is the good model lah, maximum or minimum. Okay, experiment design. Yeah, okay, this one is in this experimental design, they will give you this is not important, not important. Okay, just to provide reasonable distribution of data point. Okay, meaning when you do the response surface, it will give you your experiments run. Where is the point? Okay, model adequacy. Okay, whether the quadratic model that you put in is fit or not. Okay, it allows the experiment to be performed in block. Okay, this blocking is normally when you have too many experiment runs. For example, you have 20 experiment runs and your lab only can, every batch only can run 10 experiments. So you will do the blocking, 2 block. First batch 10 experiment in first block, another 10 experiment in other day will be second block, something like that. Okay, the design it allowed the design of higher order. Okay, is the quadratic model lah, and okay, sorry, this one. So it can provide internal estimate of error. This one is the pure error. Okay, the pure error. You in the ANOVA, when you calculate, do you remember when you calculate the sum of square error? Yeah, the 3-level factorial design, you can calculate the internal estimate of error. Okay, another one is estimate the model coefficient. Okay, is the one like y equal to coefficient x1 plus coefficient x2, something like that. Yeah, so this is the coefficient. Provide a group profile of prediction variance. Okay, this is for prediction lah. Like I mentioned, in the response surface, it can predict the optimum condition for you. Yeah, and also it can tell you which experiment is the outliers. For example, you run 20 runs, then it will tell you, okay, run 13 is the outliers, yeah, or the missing value. Okay, it can tell you. Then you do not need to run many experiment runs. For example, you just need about 20 runs to optimize 4 factors. Yeah, something like that. Okay, ensure simplicity of calculation. The software will calculate everything for you using the ANOVA. So the design of response surface methodology, you can use the CCD Box-Bacon, okay, 3-level factorial, okay, This three is the most. This is the conventional classic one. Yeah, these two is the currently more popular one. Okay, three-level factorial design can screen up to 4 factors. Okay, then they have some replicates at the center point using the quadratic model, but the disadvantage, they need to run many experiments. Okay, CCD, they are using quadratic model as well. It actually created from two-level factorial design with additions of center point and axial point. Yeah. Is less sensitive to missing data. For example, there is 20 runs. If you miss the run for 1 or 2 runs, you only have 18 runs. They're still able to predict the optimum condition for you. Yeah. But CCD, they are using 5 levels. 1, 2, 3, 4, 5. So they are using 5 levels instead of 3 levels. Okay. BBD is more simpler, using quadratic 3 levels, so less experiment runs. Okay. But the problem is it is more sensitive. If you have missing runs, then the CCD might give you error. Yeah, it cannot prove CCD. Yeah. So these are some summary from. Okay, like just now I say CCD got 5 points, 5 level. So center point, this is factorial point, and they have another one is called axial point, or we call it alpha, positive alpha and negative alpha. Negative alpha. So yeah, positive here, negative here. Yeah. So negative 1, 0, and positive 1. So they have negative alpha, negative 1, 0, positive 1, and negative alpha, 5 levels. Yeah. Okay, central composite not important for your knowledge only. From here on, all just your knowledge. Okay, so in BBD, they predict all the things at 4 points. Okay, this is BBD. In CCD, they predict these 4 points, and they have, because they have axial points, so they will predict this here. Yeah. So when you connect all, it become a circle. So we call it rotatable. So it able to detect those empty area that BBD cannot do. BBD just like this. Yeah. That's why when there is axial point, they have their predictions capability is higher. Okay, more accurate. The precision is higher. Yeah, they have better prediction. So this is version 7. If you use CCD, you can check on the numeric factor, categoric factors. Okay, you can check for many factors as you want. Okay, for example, for CCD, you can see where you can choose the rotatable. Okay, so optimizations able to give you improvement compared to the one, for example, you have the original recipe. So when you do the optimization, you're able to improve your current recipe. For example, it can in fermentation, it can use to improve the enzyme, right? The growth of bacteria, enzyme activity, all this. So how many times they can improve? For example, 3-4 increase after you do the optimization, 2-4 increase after you do the optimization, yeah, or 20 to 36% increase after you do the optimization. This is how wonderful this RSM is, optimization. Okay, after the optimizations, then you will do the verification, because they will just give the prediction. So after the predict, you have to verify. So if you do not verify, then you cannot tell people the model is valid, because you are not confirming the model. So if you run a single verification, meaning you just run one time, so still okay, but because you are not running replicates. Normally we need to do triplicates to confirm. Okay, if you just run one time, then it might not give you a very strong justification. But unless your budget and time is limited, then you use single observation. If not, then you need to run a few replicates, okay, to make other people know your model is valid, and the risk of being wrong is the risk become lower lah. Yeah. So you will do average of, for example, if you triplicate, then average of 3. Yeah. If you do 5 replicates, then average of 5. Yeah. Then after you do the optimizations, then you, for example, here I do 5 replicates. Yeah. Then it will tell it will tell whether this average of activity or the values is when compared to the predicted value is okay or not okay. Yeah, whether is if just 10% difference or 5% difference, then your model is good. Yeah. Okay, the summary is you do the screening, characterization, method of steepest essence, optimization, then final confirmation. This is important, this part. Okay. Yeah, that's all from me. Any question from you all? Any questions?
No, doctor.
No, okay. If no, then we will end our session. Okay, good luck to you all. I will see you on next week. Please install your Design Expert software in your laptop and bring to the class. Okay, we will do the I will show you the practicals. Then we will do the assignment together. Yeah. Assign your group. Thank you. See you all. Bye.
Thank you, doctor.
Thank you, doctor.